There we go. So last time we were talking about this lab. This is the material that you're supposedly going to learn here, although you're learning more than this. But this is somewhat of a summary here. And the strategy that I have to you to go through this learning, to learn about these topics, the notion of a data type, distinguish between an int and a double. I'm not just lecturing with PowerPoint slides, okay? So I could do that. I could craft PowerPoint slides and talk to you about what things are. That's one way to do it. The other way to do it is to focus on problems, and that's how I run the class. I throw out a set of problems to you and let you work on them. And these problems, and I give you practice problems, so I'm going to give you the same problems in the exam format. So I'm going to give you practice problems to work on. I'm going to talk about those in class. So we're going to be problem-oriented. And then the topics that we need to cover, I will cover in the context of working out the solution to these problems. All right? So some of the problems, I'll show you the complete solution. And you could just memorize the solution and produce it for your lab, or else you can go through the thinking process and with some familiarity with what I show you, you can try to recreate the steps involved in solving the problem, and that's better for you. And then you're practicing the problem solving. Now, when I give you the exam, I'm going to give you unique problems that you haven't seen. So you'll need to practice solving novel problems. The exam problems will be similar to the ones that you're working on now. So they will not be radically different. They'll be the same type of problem. But to be able to solve them, you have to be able to do these lab problems, not from what I show you, by copying what I give you, but by you going through the problem-solving process on your own and coming up with that solution. If you get stuck, you go back to the lecture and the notes that you've recorded or the video that I record here. And then see, oh, that's how he does that. That's what he says about this. So that's what an integer is. And so all the information is going to be there. You can refer back to it. But ultimately, you need to practice that skill of problem solving on your own, through your own sort of memory, the things that you need to know for the exam. That has to be committed to memory. There's not a lot to memorize, I got to tell you that. If you forget something like, oh, what's the name of that function to produce a random number? I mean, I'll give that to you right in the exam. Just tell me, you don't remember the name of those? It's REND. I don't have any trouble with that. The focus is problem solving. The focus is not memorizing things. You're not going to memorize algorithms. You don't even have to memorize syntax. If you can't, you'll know the syntax because you'll have so much practice with it. If you do the work conscientiously, that you will simply remember this stuff. And if you forget, I will tell you in the exam. But I won't solve the problem for you in the exam. That's the essence of what you need to learn in this class. So let's get back to the work. And I think we were looking at this exercise 2. We were talking about this, right? So you need to, let me show you how to submit your answers to this. So on purpose, I made this look as if you're taking the exam. So it's practice for the exam. In class, you'll sit down, I give you a sheet of paper. You're going to write down your answer there. But for the lab, what you do is maybe create a text document, like a Word file or just any kind of a document. And I'm going to show that to you here. I'm going to call it exercise2.txt. I use the extension txt because it's a common extension for files that contain character data. And so let's answer problem 1. Now, of course, I'm going to put my name up here. Let's answer problem 1. When the code in figure 1 runs, what does it output to the console? So we need to read this. We need to analyze this. What does it do?
Creates integer I and makes it set to 0.
Creates an integer I and initializes it to 0. That's right. That's the first step. Let me take this out so it's a little easier to read. I'm going to just paste it in here. I'll put it up here. There's an indent here, and the purpose of this indent is to show that these two lines, here are substatements in a larger parent statement. This is the parent statement. While I is less than 7, see out 2 times I and then increment I. Repeat that and then check the loop condition and repeat until the loop condition becomes false. So this thing that I have highlighted right here is a single statement. It's a compound statement, but it's a single statement. It's a statement comprised of substatements. It's a loop. It's a loop statement, a while loop specifically. It has 2 substatements. This is the first substatement. This multiplies the value in I by 2 and then sends it into the standard output stream, which ends up getting displayed on the console, or depending how we run the program, maybe into a file. And then after it does that, then the program increments the value in I. And then after that, the program evaluates the loop condition. It says I, compare it to 7. Is I less than 7? If I is less than 7, the loop condition is true. We continue with the loop. We will do the 2 substatements again. And notice the last substatement in the loop is incrementing I. And that's why we eventually exit the loop, because the loop condition is dependent on I. As soon as I gets to be equal to or larger than 7, it never gets larger than 7. As soon as I hits 7, the loop condition becomes false. Do you see that loop condition is false when I is 7? Because this loop condition is that I is less than 7. Let's replace I by 7. 7 is less than 7. Is 7 less than 7? No. So the loop condition is false. When the loop condition is false, the program considers the loop statement to be completed. And the program will go on to the next statement. And the next statement might be something else. All right, whoops. The next statement could be something like, I don't know, done. So look at the program. Actually, this, if you can think of this as a program, or it's a piece of a program, like a code snippet, we could say. This, we'll call it a program for now, because this could stand as a single program, although it needs to be inside of a main function. But this code here has 3 top-level statements. The first statement is this declaration and initialization of I. In computer science language, we say this is a definition of I. So a definition is both a declaration and an initialization. The second statement is the loop, which is a compound statement, including substatements. And the third statement is this, which outputs done. So you have to train your mind to sort of parse, to understand, to read, and understand programs like this. This is how you read through code and structure it in your mind and in your understanding. The first line, let's go back again. There's kind of like 2 things going on here, actually. When I see that, I see 2 activities. The first activity is remember the compiler takes this code and translates it into machine instructions, which is then loaded into RAM, and then execution, this program pointer is set to an entry point in those machine instructions, and the CPU starts running and so on. And that's a detail we're going to have to be fuzzy about. We have courses that teach that. All right, there's a course called 313, Machine Organization. It talks about how the CPU works, how does the CPU, how do registers work, how do programs that are represented by sequences of numbers, how do they run inside of a computer? Okay, but we're not going to get into that level. That's they call that a lower level. We're at a higher level. And so what we do is we make simplifications about what's going on underneath us. So that's one of the arts, one of the techniques that you use to master this your ability to function at this particular level. You have to create the right ideas and models and abstractions about what's going on. And they're all simplifications. So let me explain to you the abstractions that I make when I see this line. I say, well, first of all, there's two things that are happening here. We're telling the compiler to allocate memory to store an integer. That's this. Allocate memory to store an integer. And from this point on, let's refer to that memory location as I. That's like the name of the location. So when we refer to I here, and I here, and even I here, and all of these uses of the letter I, it's all a reference to this allocated memory in RAM that's 4 bytes, because an int is 4 bytes generally. And this integer, actually, in a 64-bit machine, is an int 4 bytes? I don't even know that. I'm a computer science professor. How would I find that out? See, I don't teach that. I don't teach machine organization. I mean, I studied a long time ago, but I can't remember. And this was before 62-bit machines were around. Yeah, size of int is 4 bytes. Actually, we can do it like this. This is easy, actually. We can do, let's create a little example here. This is going to be very easy. We don't even have to look it up.
Bless you. Thank you.
So here we have main. I'm going to call it t.cpp. Size of, this is a function or an operator, size of, what's the size in bytes of the data type int? And let's print that out. And we don't need this, but we need IO stream. 4. Okay, 4 bytes. I mean, it's 4 bytes on this machine, and this, generally, is it going to be 4 bytes? I think probably. That was my initial assumption. So I'm pretty sure it's 4 bytes. But I might want to talk to some of my colleagues, make sure that's absolutely right. I think the way the language C and C++ is defined, int, is there's not a predefined number of bytes. The int was originally supposed to be dependent on the hardware, the number of bytes that were used to represent an int. So I don't know what has happened over the years with that, but I think it's probably safe to assume that an int is 4 bytes. Although you see in newer programs, you won't see the data type int used a lot. You'll see things like, you'll see something like int 32, which would be like an integer with 32 bytes, something like that. That would be like the data type. I'm not going to get into that any more than I have. So coming back to here, so here the compiler is creating code that's runnable by the machine that ends up creating an allocation in RAM of 4 bytes to store an integer. And then it does something else. It says, also compiler, generate whatever instructions you need to generate to initialize those 4 bytes to represent a 0. So it's initializing I to 0. Now the next line is more complicated to understand, so we'll go more slowly on that. And then the third line, the third statement, is we take the string done, and it's called a string literal. We're using the data itself right in the statement. We're not using a variable that represents the string done. We're using the string done itself. Call that a string literal. And we're using that. That appears on the right-hand side of this output operator. So basically, we're telling the compiler to generate machine instructions that sends this string, the bytes that comprise that string, into the standard output stream. Let's look at the loop now. Oh, now, by the way, the exam question is to what? What does it output to the console? Well, this is the only place that it outputs something, right? And this output operation is inside the loop. So we're going to repeat this. So we'll probably print several numbers. Start with 0. We're going to start with maybe a 0, then it'll print 2, 4, something like that, right? Well, is it going to print 8? Is it going to print 6?
Because I is 4.
It's C outing 2 times I, and it's running as long as I is. It's not outputting I.
It's not reassigning I.
It increments I here. See? It initializes, so the first time you come into the loop, I is 0. 0 is less than 7, clearly, right? I is 0. And then here, I is modified. This line here does not modify I. It reads I. It reads a state of I. It does not change I. Here we multiply I by 2. But we don't modify the storage location that I refers to. We just read from that storage, multiply by 2, and use the result. We're not modifying I here. Here, we are modifying I. We're increasing I by 1. That's what that operation means. That's the increment operator. So you...
I noticed that sometimes people use plus I, and sometimes they use I plus.
Yeah, this is called a pre-increment, and this is the post-increment. They work slightly differently, and we'll talk about that in the context of another problem. In this problem, they would be equivalent. So this is not a good scenario to talk about the difference. I like to use this one. So what is the answer? What does it print? Does it print... Does it...
Yeah, it prints 10, 12, 10, 4, 6, 8, 10, 12, 10, 12.
It stops at 12?
Yeah.
Any other ideas? You should all have a solution in your head. What about 14? Why doesn't it print 14?
Because it tests the loop, and then there's one code. 7 is not less than 7, so it doesn't.
Exactly. This line will never execute when I is 7. When I is 7, the loop condition is false. What if we did this?
Then it's only
Now what's it going to do? Is this string correct now? This sequence?
no.
Increments I before.
Because basically we gotta take off the 0, right?
Yeah.
Now it's okay? Everybody agree?
It's not.
2, 4, 6, 8.
It's not
Are you all ready to do this on an exam? You got to get ready. You're going to practice this. Well, let's simulate you at home right now. And you go, I think it's this. Let's see. I'm going to send an email to my instructor just to make sure. Nah, that's going to take forever. I'm going to ask my friend. Well, what if my friend doesn't know? I'm going to create an experiment so that beyond a shadow of a doubt, I know the answer. Let's create that experiment right here. I used to use spaces for indents, and now I use tabs. We can just run it. Let's see what it does. Anybody want to make a bet? Anybody want to bet against that? $1? I'll bet $1. Huh?
What about the 12?
Get rid of the 14.
Is this right or wrong? Actually, I didn't think about it very carefully. Huh?
So click out 14.
Take the 14 out?
Yeah.
So this is what people feel will be printed. Is that right? Anybody think otherwise? Huh? Remember, I changed this. Oh, I'm sorry. Oh, that's the original one, right? That's the one I wanted to look at. Okay, so
That's the original.
we're going to go to the original one. So we need the 0, right?
That's not the original one.
Sorry.
That's it. So you need the 0 in there.
Now you need a 0.
We got to have a
And then
0.
which code did you save though to run?
I don't know.
You used the
Oh.
new one.
All right. Look at that. It's so easy to create a bug. All right, so we think this is going to be 0 through 12. All right, let's try it. What? ASCII characters are not allowed outside of literals. Oh. Let me tell you the problem. I copied it from a PDF. This is a big problem. And you can't see, but there are weird characters in there that are being misunderstood by the compiler. This is a problem. I got to stop using PDFs for source code. Let's take a look. Let's open this. Let me try this. Let me see if this. Here's Xcode. This is the. Oh, wait a minute. I gotta remember my password now. What's my password? I get 1 million passwords. Got it. So that, what the documents, when you see a document and you see characters in the document, in the file internally, those characters are represented by numbers. And there are different systems of representing characters with numbers. There have to be. Originally, there was not too many different systems, and 8 bytes were good enough to represent characters in English, and then some European languages, and then we got to things like Chinese and Hindi and other languages. 8 bytes is not good enough anymore, so we had to solve that problem. So we needed different kinds of character representation systems that relied on more than a single byte. And things have gotten very messy ever since then. And that's a big topic to deal with. And I'm not going to get into it too much. Oh, look at that. Here we go. And what's going on here, I believe, is that when I copied in my browser from that PDF document, that, trying to make that bigger, that there are some numeric values that were used to represent things like semicolons and spaces that the compiler is not interpreting as semicolons and spaces. I think I had this problem last time, and I don't remember what it is. How can I? There's a way to view. Oh, show invisibles. I think this is it. Do you see that? These are. Let me get the view here. How can I increase the font size? This is not very convenient. I just have to click on this. That's not working. But look, let's do this. Look at this symbol is for space. I'm gonna just hit my space bar. That looks okay. So the invisibles look all right here, and these are spaces here. And maybe it's that semicolon. Is that what it could be? Well, when I hit that semicolon, then all of a sudden this appeared. Looks pretty crazy. All right, let's do this. Take the tabs out. I think it might be the semicolons. I'm going to try that first. I'm going to replace all these semicolons. I just replaced the semicolons. It worked. It was the semicolons.
So then we just take out the semicolons?
No, he just replaced them.
Oh, so you just oh, okay.
Yeah, maybe you should type this out rather than copying and pasting. Unless you want to think about this problem or try to solve it. Maybe I should get rid of these PDFs. Now I'm going to demonstrate this again. Watch. I'm going to copy the semicolon here. Watch this. Copy that semicolon right there. Okay. And I'm going to insert it in here. This one right there. Okay, I deleted the semicolon. Now I'm going to paste in from my clipboard that semicolon I copied. I'm going to save it. You see that? Look, there's the problem. This is the line number, line 9. Okay, column 14. And it's complaining about that character right there. Non-ASCII characters are not allowed outside of literals and identifiers. So the PDF document is representing that semicolon as using a non-ASCII encoding, a non-ASCII code value.
So if you just press backspace and then type an actual semicolon.
What's that?
If you just press backspace and then type an actual semicolon.
Yeah, hit backspace and type the semicolon in. That's right. That's one way to do it. Something to watch out for. Oh, let's run this thing. Two through 12. Oh, you know, it doesn't have the, the line. It's not clean. So it just, if I do this, let's just print a space here. I omitted this from the lab, from the exam, because it's just too much extra detail. I just want you to focus on understanding the logic of it, not the extra little details there. So I just printed space here, and a new line at the end. And so that should look better. Nope. What did I do? I'm in the wrong place here, right? Yeah, I did not do that correctly. It's here. I got to guess here that some of you might find this fairly interesting, and but many of you think this is going to be pretty boring. Is that interesting or is that not interesting? Just going through this process and asking the questions and trying to get it to work and developing that understanding. Now you know about character sets and representing characters in using different representation systems, and copying and pasting is something that interacts with that issue. Yeah.
Is this something that could potentially happen only in PDFs, or is it something that could potentially happen in email? If I have a friend,
It can happen in email, and it can happen in web pages for sure.
okay, well that's let's say a friend emails me the code, right? And I'm
Yeah.
just like, oh, well, I just copy and paste it into Node++ or whatever, and you were an online compiler, and the online compiler can't read it, It's a perfectly valid code, but because of that ASCII error, is that something you might run into emailing?
I've never seen it happen in an email. I've only seen it happen in a PDF. I've also seen it happen in web pages.
Okay, so that's not something you would be able to run into emailing you
I think emailing, you're safe. If you send an attached file, that's safer. But I've never seen it. Yeah, when you send the files to Jaron, make sure that you should send them as attachments. Don't put them in the body of the email. I haven't seen the problem in emails, but it may happen. So now, in this is what I want you to submit. Here you've got your answers in a file, and you'll send these to Jaron and CC me. Then you'll have another answer, whatever it is, and just put your answers in here. And then send this to Jaron as an attachment, CC me.
And that's in a .txt file, right?
Yeah, or a doc file. Jaron is using Windows. And I can open a doc file as well. So it could just be a text file. Actually, you could send this in the body of an email too. That's all right. This is not source code. We're just going to check to see that you got the answers right.
Okay, so there's just okay.
Now this is exercise 2 of lab 2. So exercise 2 is to answer all of these little problems. So there's a lot of small problems to do. Let's look at some others. Now, so today we learned about loops, right, and loop conditions. And you should be reading along in your books. Now, I'm not going to tell you what to read, but it's obvious what you need to read. Now, look at the chapters, look at the contents. You've got to read along with it. They're going to talk about while loops and for loops, data types like an int, and that it's 4 bytes. There's going to be discussion about how the program is represented in memory, how many bytes the different data types occupy, and so on. So please keep up with the reading. Oh, here's another one here. Rewrite the code in figure 2 so that it uses a while loop rather than a for loop to accomplish the same output. So now I get to talk about for loops. And I'm going to make the same mistake as before. Well, actually, I'll just type it in there. Let's look at the answer for 2. So the problem, I'll copy that. Problem. All right, that's the problem. So this is a for loop. The problem is to rewrite this using a while loop instead of a for loop. But what is a for loop? let me explain what a for loop is. A for loop, similar to a while loop, has a block of statements, substatements, that are executed repeatedly as long as the loop condition is true. Oh, remember, in the while loop, the loop condition was just here inside these parentheses. See, that's called the loop condition. That's the thing that you have to evaluate to see whether it's true or false. And if it's false, you have finished running the while loop. And when it's true, you haven't finished, you gotta execute the substatements. Here, in this part of the syntax, that this is the loop condition. I is less than 7. And actually, there's 3 sections here. There's the first section, which is terminated by a semicolon. There's the second section, which is the loop condition, terminated by a semicolon. And then there's the third section, which follows that second semicolon. The first section is the initialization. This is a statement that runs the first time when execution reaches the loop. When execution reaches this for loop, it's going to initialize the variable I to 0. And then it's going to evaluate the loop condition. It could be that the loop condition is false right from the beginning. If we initialize I to 80, we can do this. We will never print anything because the loop condition is never true. So we'll never print the substatements. Well, I will never execute the substatements. But that's not what we have. Here we have I being initialized to 0. Now when we get to the loop condition, 0 is less than 7, so the loop condition is true. So we run the statement. So there's only one statement. So we print out 2 times 0, which is 0. But this hasn't come into play yet. This is the end of loop operation. This is also a statement. Just like this is a statement.
So it's not going to increment I before that runs.
Right.
See how it runs.
When you finish executing the substatements, the end of loop operation is executed. Incrementing happens after that cout operation. That's it. So how would that look in a while loop? Well, let's think about it. Initialize I to 0.
While I is less than 7.
That's right.
And then brackets. Open bracket. C out. 2 times I. Semicolon. And then plus post I.
That's right. Good. Oh, I need the L in there.
Yeah, I was going to say, like, it's.
This is one style, put the bracket here. The other style, which I've been intending to use lately, is to put the bracket there. Those are both common styles. This style here is more common. But the other style appears a lot as well. I think the book may use the other style. And, when you write programs, what I want you to do, you don't have to stick to one style. But in your program, any program that you write, you need to be consistent in your style. So don't mix these 2 styles together in the same program. So if both of these were in the same program, you should be consistent in how you organize the code. So if your braces come at the end of the line, rather than start in a new line, then be consistent with that throughout your program. And the reason for that is that it makes it easier to read the program. Yeah.
It seems like you can accomplish the same sort of thing with the while loop instead of using the for loop. But when would a for loop be?
Well, look at this. The for loop, the while loop is like your basic loop, okay? But the for loop is, you could call it syntactic sugar for the while loop. it's more compressed. Look, this is 3 lines, including the closing brace. This is 1, 2, 3, 4, this is 5 lines. What's easier to read, this for loop or these 5 lines? I mean, at your stage, just starting out, you might pick this one here. But ultimately, when you do this a lot, you will see that the for loop, you can read it faster. So it just has to do with readability. Every while loop can be written as a for loop. Every for loop can be written as a while loop. They're interchangeable. Yeah.
Will for loops always be written in like 3?
Yeah, always. This is a requirement. A for loop has 3 sections: initialization section, a loop condition, and an end of loop. We could do this. Like, this is fine. The while loop, the compiler will accept this. We could do that. And not only that, we could do this. We could take the initialization out as well. Now, the initial instruction is empty, and the compiler is okay with that. And the end of loop operation is nothing. The compiler is okay with that. But the loop condition, you have to have a loop condition.
You would still keep the semicolon up there?
You have to have the semicolons. Some newer languages, you can omit the semicolons, and they'll take it, but not in C++. So the answer to the problem is, oh wait, we didn't do this right. Well, that's because I cut up here. Yeah. There it is. So that's the answer to the problem. This is that for loop written as a while loop.
Okay.
And if you wanted to make extra sure, then you would run the code. You would run the for loop, see what it produces, and then code up the while loop, run it, see what it produces, and then you could check your work. Now, on the exam, you won't be able to check your work. So you have to be very thorough. Here's a mistake that you could make studying. You could simply say, well, why? I'm going to save some time. I want to check my work anyway. I'm just going to drop all the code in there, run it, and see what it does. Then what are you going to do when you get to the exam? You don't have anything to run the code on. So you have to practice reading code and analyzing code. Don't make the mistake of just typing it in there, running it, and writing down the answer. That's a mistake. All right. Let's look at number 3. How many times does the body of the for loop run in the code in figure 3?
Yeah.
It's figure 4.
Huh?
That's figure 4.
One more time?
That's figure 4.
That's wrong figure.
Oh, thank you very much. Thank you very much. Let's do 3. Looks like the tabs are not coming through here. There we go. How many times does the body of the for loop run? Well, look, we declare a k, initialize it to 100. That's the first statement. And then we only have 2 top-level statements, and then we have the for loop. That's it. Okay. So how many times does this thing run? What's the answer?
100.
100?
Million.
100 times. That sounds right to me. Yeah, it's good. That was fast. What about 99 or 101? Those are possibilities, right? This is called a one-off problem. You have to check, make sure you're not off by 1.
You're starting
If you're starting at 99.
Yeah, if we started at 1, it would be 99. But what if I did this? Okay.
but it'll be 101.
That's 100, right?
Is there like a formula to calculate? Like, let's say I was like 30. Like, is there like a quick way to find that out? I mean, like I was 30.
I was 30.
Oh, I was 30.
K was still.
Oh, if you initialize I to 30,
Yeah.
and this is 100. Actually, you know, K never changes, so actually, it's a little bit of a trick question there. We don't even need this. Just put 100 in there. So, how many times does this loop run? 70?
71.
70 or 71?
71 because you're counting 30.
Yeah, you're starting at 30, right? But what happens if you do this? That looks like 70. So it would be 100, be the loop limit minus what I starts at. If you use strictly less than, but if you use less than or equal to, it would be that equation plus 1. And I don't know if it's useful to memorize that. I have never used a formula like that to figure this stuff out. But maybe a formula is better. It's an off by 1 problem. It's very tricky. Counting starts here at 30. See, here, let's suppose this is too hard for you to sort of get, right? So let's do it like this. Let's do, that. Let's make it simpler, and then we can generalize from it. We really want 100 there, but let's just use 31. Now maybe then here, I think what I end up doing mentally is I figure a formula out with a simpler instance and then use that. So this loop, how many times does this loop run? 2, because I is 30, right? So 30 is less than 31. That means this runs. And then I is incremented to 31. Oh, wait a minute, it only runs once. This runs once.
Equal to or greater or less than it would run.
Yeah, if it was also equal to, then it'd be twice.
This only runs once. So look, the formula at this point we have just determined is that it's 31 minus 1. I'm sorry, 31 minus 30. That equals 1. And that's how many times it runs. And it's easy to see that if it was 32, this formula, then it's going to run 2 times, right? We let I go 1 more higher. What happens if I is initialized to 100? Can we just roll along here and do the same calculation? Don't you feel some confidence in that? After checking with the smaller instances, and then it verifies your formula, and then you can apply the formula to the larger number. So the answer to 3, so this should be 0, right? I better look at this. So this K, look at this. K is set to 100. K never changes. We don't modify K in here at all. So you can just sort of forget about K and just use 100 there. Start at 0. And the last time the loop runs is when I is 99, because the last time the loop condition is true is when I hits 99. If you start at 0 and you go to 99, you have I has taken on 100 different values. I takes on 100 different values each time that loop runs. And when I takes on the 101st value that it takes on, which is the value 100, the loop condition is false. We don't execute the body of the loop. So no, we don't need this stuff. You know, when you're done that, that's the answer. 100. Okay, figure 4. What does this output to the console? Anyway, this goes on and on. Maybe I don't want to go over this too much. Let me think. Should I do all of these?
Yes, you should.
What time is it? And then we also have random numbers here.
12:52.
Huh?
It's 12:52.
12:52. Let me go back and, Unicode. This is a very tricky problem, exercise 4. When does this lab due? Do we have time? Oh my
It's
gosh.
due on Wednesday.
It's due on Wednesday.
For,
For the people
for
who-
us today, it's due on Wednesday. For the people
Oh.
with lab on Wednesday, it's due on Friday.
I think that's.
No, it's just due on Wednesday. I mean, that's it, right? Or is it due on Friday?
I believe
It's only
the
one
last-
day. It's only one day it's due.
Yeah, it's
Okay.
Friday.
It's Friday. So if you lab on Wednesday,
It's
you have
due
till
on
Friday. It's
Yes.
just due on Friday. That's it.
Thank you.
But the Monday, the people of the Monday lab, it's
Are
due on
Wednesday.
Wednesday.
I
That's
don't
what you
think so.
decided last class period.
Oh, no. I don't want, well,
That's,
Miscommunication.
that was you.
miscommunication. I want to, if we need to push back the lab, we're going to push it back for everybody so it's on the same day. It's too confusing. By the end of the class, you can actually attend either lab section. You know, there's usually open seats. You just go to the lab sessions that are convenient for you to go to. You don't have to go on your assigned day. I don't keep attendance or anything like that. The lab is just there for you to help you with these problems, working with others, and working with me, working with the other assistants that are available there. So I have here October 8. Is that Friday?
That's Wednesday.
So we can make that October 10. Okay? I will change that to October 10. But everybody has the same deadline. All right. What are we going to do now? So who just request a problem. What do you want to look at next? Which one of these problems? Do you want to look at? Huh?
The one is like tricky.
The tricky one, the last one.
No, tricky one. All right, unit conversion. This is hard. Write a console program that converts meters into feet and inches. This is a very tricky problem. The program starts by asking the user for a measurement in meters. All right, I'm going to write code just to do that right now, so that we don't have to lose time on that part. So let's see, I'm going to copy main to ex4.cpp. We're going to prompt the user for meters. We'll read it into a variable m. And we need to declare m. So it's a floating point value. How many meters? 1.2. Enter. So right now we have this program that prompts the user for a number of meters and reads it in. That's all we're doing right now. All right, so basically the program starts by asking the user for a measurement in meters. We did that. Okay, that is done. The program should accept a floating point number. We did that because we declared m as double precision floating point. So we've done that. After getting the number, the program computes the number of feet and inches equal to the specified number of meters. The program outputs feet and inches as whole numbers. The program should round the number of inches correctly. Test that your program produces the following outputs for the given inputs. All right, so we're going to end up computing, let's just start with feet. So we'll have it, and it's going to print a whole number, so integer values. So let's declare a variable feet. And actually, to convert meters to inches, what do we do? To feet, rather. Like here it shows it. So how many meters are in a foot? Or how many, let's see.
No, 1 foot is equal to 0.3048 meters.
Yeah.
Is that exact?
It's exact.
Really?
Maybe.
Not sure about that. That's what I have here, 3.
Oh. So we use yours, or we use the one that Google tells us?
It doesn't matter, it's just a rounding.
This is rounding.
It's rounding to the nearest.
Look at the source code.
How many feet in a meter? Oh, there it is. So,
I thought you feet on a meter. 1 foot is.
say it again?
1 foot is 0.304.
The same number we got.
This is the number they give us here for going from, so 1 meter. So do these two numbers agree with each other?
Yeah.
And so I'm using this value here.
Because you're saying,
Oh, this is 1 foot because it
Yeah.
rounds it down. All right. All right, let's try that. So the input, so we're going to put in that many meters, right? So let's see if that works. So these are feet. Let's change that to meters. Let's assume that this is right? So that's a meter and that's a foot. Yeah, so that rounds to 1 foot. Okay, so that's what we want to output right there. All right, so and the conversion, let's see, is, that's not the right one. Which is the one we looked at, this one here. So we have meters, and so let's see, how do we convert to feet? So we have that many meters, and so we have to divide by that, right? $3,048. Am I doing that right? Let's do it like this. I'll do it like this. I always got to think carefully about this. So 1 foot is that many meters. So that's right. This calculation is right. Does that, anybody disagree with that?
Why is it divided? Why is it divided by that number?
Oh, it should be multiplication, right? Is that right? Let's suppose we have 1 meter, right? A foot is smaller than a meter, so we better multiply. Okay. All right, so there we go. We multiply. So let's suppose we have 1 meter, and that's one foot.
yeah, because you put M
out, and then M, and then foot.
Oh, that should be feet.
Yeah.
Thank you. So 1 meter is 0 feet. Okay, I'll round it. That's right. It should round it down. This is good for us, right? And 2 meters is 0 feet.
Yeah, that's, no,
It
I'm
should be
trying,
more feet.
Wait a minute.
yeah.
This is not right. 1 meter should be 3 feet. What are we doing wrong?
You're multiplying by the wrong number.
Yeah.
You need to multiply by 322.
That's what we got to do. I had it right the first time. 1 meter is 3 feet. That makes sense, right? Okay, now we're back to reality. All right. And 2 meters, 6 feet, whatever. Now, look what happens here. See, this is division, and this is called floating point division because the numerator and denominator are both floating point numbers. So the compiler interprets this symbol here in that context as floating point division. And if the left-hand side and the right-hand side were integers, the compiler would interpret that as integer division. Well, so now here, look like this. If we made this a double, watch this. If we made this a double, then we'd get a floating point value. See that? But we want whole numbers of feet. So we're going to declare that as an int. And what the system does, what the program does, is it takes a floating point number and converts it into an integer value. How do you convert a number with a decimal point into a number without a decimal point? You got to lose information, right? So, when humans talk about things, we would round this. We would, round the number. We would do the conversion and round up or down. If it was 3.9 feet, we would say 4 feet, right? But in code, when you try to take 3.9 and store it in an integer, what the program does is it truncates. It doesn't do rounding. It will discard the 0.9, and you're just going to get a 3. So if you want to get rounding, you have to add 0.5 and then get a new double precision value, a floating point value, and then do the truncation. But we're not going to round the feet. We don't want to round the feet. We want to round the inches. So we have the correct number of feet. We basically want to discard the fractional component. Let's get the number of inches. How many inches? And I'm going to take this out as a double, start with a double. This is the number of inches that are remaining after we remove so many feet. So I have the number, and we do it like this. Let's see how we're going to do this. I'm going to change this around. Now, when you're coding and you're developing solutions to things, you've got to be flexible. You've got to reorganize your code. It's called refactoring. You got to keep your code in a state that you can understand. I'm going to store this as a double. And when I print this, so this is a double. And I'll have another number, which is an integer. I'll call it ft, say.
Bless you.
Let's see.
Feet. I'll call it this. Oops. So here is where we do the truncation, where we take a double precision value and we store it in an integer variable. So we're going to truncate. Now I need this representation of feet with the decimal value. I need that to do my next calculation. Why this should be like that. So the number of inches, or the number of feet, minus how many feet did we take out? FT is how many feet we're going to display to the user. So if we take our feet represented as a floating point value and subtract out the integer number of feet we're going to report, that will produce that the decimal component. But that's in feet. So that has to be converted to inches.
Aren't you only then converting just the decimal part of the inches?
Yeah, we do, but we need to round it. I want inches to be rounded up or down. I'm getting there. So that's right. This is the hardest problem in lab 2, by the way. So we're doing the hardest one. Let's print now the number of inches. So we're going to print the inches, and we're going to keep it as a double precision value just for now. We'll switch that in a minute. All right, so 1 meter. What's 1 meter? 1 meter is what? 3 point, this times 12 is, right?
You're missing your,
Yeah, you missed this.
3 inches.
You
you're
missed
missing your
the 3 in that one.
Before the
It's a
decimal.
3 point.
Oh no, I wanted to chop that. I wanted to chop that off, right? That's the 3 feet, see? So we're going to report 3 feet, and then we're going to report how many inches beyond 3 feet. So this decimal. This is what gets truncated when we try to store the floating point value in an int. So that's to isolate the 3, and then this is the part of it which is in feet, needs to be represented as inches. So we're going to multiply by 12. So that is 3 inches, and we'll end up rounding that down just to keep it at 3. There it is, right? Here's the 3. It's the same number. We're almost done. But here's the problem. What happens if we're doing 2 meters? Then the number of inches is 6.7, so we want to round that up to 7. And when the inches is 3.3, we want to round down to 3. So how do we do that? Well, we add 0.5. That'll do the rounding for us. You'll see the 6.7 plus 0.5 gives us 7.2, and we're going to discard the 0.2. We're just going to get 7 inches. 7 inches, that's this number rounded up to 7. That's what we want. But now we need to omit this. Just want to display a 7.
Make an integer.
We could do the same thing we did for feet. Declare an integer called, say, in. I hope that's not a reserved word. And it's basically this. In might be a reserved word. I don't think it's a reserved word in C, but in C++, but it is in other languages. Let's see if we get a problem with that. There it is. Right, there it's rounding down. Let's do the final test. The input, 3.3049. 0.3049. 1 foot 0 inches. We got it. Was that hard?
Tricky,
Huh?
a little tricky.
It's very tricky, but this is the hardest in this lab, okay? But you need to think about this, play with it, get this. The key is, actually we didn't talk about integer division, but we'll talk about that later. This is floating point division, that's one thing. Also the conversion of a floating point value into an integer value that we get truncation, we don't get rounding. If we want rounding to occur, we have to add 0.5 before we do that truncation operation. All right, that's it. Oh, question? Huh?
You listed, the issues as a double, data type, or
I think you should have it.
It would display all the decimal points. And the problem says to round it up to the whole number.